All right, friends, we're talking about Math 105, Section 5.1, and today we are dealing with logarithms. And all I can say about logarithms is that they are the inverse function of exponentials. That if I have some exponential function, let's just say we have x here, and we're going to get some y, and let's say we have an exponential, let's say f of x is equal to 10 to the x. That I have an inverse function, f inverse of y. And all this is the exact same statement, but it's log of y is equal to x. So we have 10 to the x equals y. We have log of y equals x. And these two are really the exact same statement. If I say here, this is 10 to some power equals y. What is this? I have, what do I raise 10 to get y? And it's the exact same thing. When I say raise 10 to, I'm looking at some power there. Or what power of x gives us y? If I did something like this, log of 1,000, okay, friends, what am I going to raise 10 to get 1,000? Well, the answer is 3. And, we can keep playing this game. If I said log of 100, we're certainly going to get 2. And if I gave you something like the log of 537, well, you would say, well, that's between 100 and 1,000. And so we might say it's around 2.5-ish. But I can certainly put this into my calculator, and I can say the log of 537 and get an approximation, and that is a better approximation than 2.5 is 2.729974,286. And what that means, and our alternate statement here, is that 10 raised to the 2.729974,286, blah, 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 guess what? That's going to equal 537. All these are inverse functions. And actually, I'm going to do that 10 raised to that fakakta power. And we get 537 out. There's another logarithm that we're going to deal with. So we're going to have log, and that's going to represent the inverse function of 10 to the x. The other function that we're going to deal with is natural log. We're typically going to write this ln of y. And the reason I'm using y is because I really want us to focus on this inverse function idea that if g of x is equal to e to the x, that's Euler's number that we just talked about in section 4.5, then g inverse of y is equal to the natural log of y. We could also call this log base e. But it's the exact same idea. All we have is this inverse function of an exponential. So keep in mind that we have these inverse functions. And what I think we're going to do for the rest of this video is we're going to discuss some of our properties of logs. Make sure that you are not inventing new and exciting properties. I promise you, they do not need your help. And so I think to start out, we might say that we have our inverse property. And the joy of an inverse and a function is when I compose them, murder occurs, and I'm left with just the argument. So I'm going to do these for log 10, as well as natural log just so we can see how these things unfold. So the inverse property, if I do something like log of 10 to the x, it equals x. These two are inverse functions, compose inverse functions, murder occurs, left with our variable. Similarly, I can have the natural log of e to the x, and once again, we only get x back. Now, this inverse property can go both ways, that I can have 10 raised to the log x. I'm composing, now I have the inverse inside the parent function, but murder still occurs, and we're left with x. Similarly here, I can have e raised to the natural log of x, and we get just x back. So those are our inverse properties. Let's put one other property on the side here. What is log of 10 going to be equal to? What power do I raise 10 to get 10? Well, that answer is 1. And the comparable question here is the natural log of e is equal to 1 as well. Let's go one more. Let's go one more of these kind of identity properties. What about the log of 1? And the question is, what am I raising 1 to? Or what am I raising 10 to get 1? And the answer here is 0. And comparably, the natural log of 1, what am I raising e to get 1? And that's going to be 0 as well. So I might call these identity properties. But I just think that, I think they're fine because we can think about this inverse and then use the specific values, that here I have 10 to the 0 power, here I have 10 to the first. We have these rules of exponentiation, and each rule corresponds to a rule of logarithm. And so I can say that we have a product rule, that the log of a times b is equal to the log of a plus the log of b. Yeah, that the log of a product is equal to the sum of the logs. Similarly, I can have this for natural log, that the natural log of a times b is equal to the natural log of a plus the natural log of b. If you want to know about these rules, I am happy to explain them during office hours and show you exactly where they come from. And really, it takes a strong understanding of our properties of exponents, and then we're done. Similarly to the log of a product is equal to the sum of the individual logs, I can talk about a quotient, that the log of a over b is equal to the log of a minus the log of b. And just like for natural logs, the natural log of a times b is equal to the natural log of a minus the natural log of b. I think of those two inside the same grouping of rules. I think that the most important rule is about to come. And this, we could say that when we have a log raised to a power, we'll say power. If I have the log of a raised to the t, what's fantastic here is that that t comes down and it turns this exponential problem into a linear one. And the reason that this rule is my favorite is, we're going to use logs to solve exponential functions. And I don't care what a is. I can put, if a is 10, fine, murder occurs entirely and I'm left with just t. But if a is not 10, I'm able to get this exact answer and figure out what t is for any exponential equation. So let's do this for natural log as well. Natural log of a to the t is equal to t times the natural log of a. Now, there is some trash that exists in this world, and the things that you have to watch out for is when you start trying to make up new and exciting rules that don't exist. Something like this, the log of a plus b. And someone's like, oh man, I know that when I add something, it's going to come out beautifully. And this is trash. There is no rule. Right? There's no combining this. There's no taking this thing apart. If I have the log of a product, I can split that up into the sum. But the log of a sum, this is garbage. There's nothing I can do to pick this thing apart. So cease and desist your tomfoolery. Another thing that we have to be careful of here is if I say the log of a raised to the t power. Now, right now, I'm not raising a to the t. I'm really raising this whole thing to the t. There is no rule. So make sure that you are not inventing new and exciting mathematics. I promise we don't need your help, okay? Stick to the things that were given and manipulate them accordingly. I think we're going to make a second video that talks about specific problem solving with these logarithmic properties, just so that we can see them taken out for a spin.